Hey guys, welcome back. Today in this video, we gonna work on understanding heap, also implementing heap with sweep. So, if I want to go over heap, first of all, we need to know what is heap. Heap is a special tree-based data structure, uh, which is a tree, and actually it is a binary tree. But heap can be in two actually category: max heap and min heap. So if you want to go over for max heap, in max heap, the key present at the root node must be greatest among of the key present at all of its children. And the same property must be recursively true for subtrees in that binary. So for max heap, our root gonna be maximum value, and then for subtree same, so maximum value in compare of children's, and for subtree recursively gonna be the same. So this is max heap, and min heap is totally opposite. So the minimum value will be present at the top, and subtrees recursively gonna be less in compare of their children. So max heap and min heap are two main category of heap, and all of this we do for heap is to find out maximum and minimum value in our tree or in our data structure or in our array with just O notation 1 time complexity. So this is all we do. So we prepare our data structure to present us minimum or maximum value just in O notation 1 time complexity. Okay, so if we want to go over heap, of course, we need to talk about terminology and properties of heap. So heap technically is a binary tree, so terminology is very similar to binary tree. So a tree as we know, can contain known or nodes, or it can contain a special node called roots with 0 or 2 subtrees, and every edge of the tree is directly or indirectly oriented from roots, and every child has only one parent, but one parent can have two children, not more, only two children in maximum. And if we want to go, yes, the root is the entry point of a tree, a data structure, and node is a block of data. This is node, this is node, this is node in tree structure. Root itself is also a node, and leaf is a node with no children. So this is a leaf, there is no children. And level of node represent the generation of node. Root is generation of. So what I mean means that level of the roots gonna be 0, level of these two nodes gonna be 1, this gonna be 3, and go on until we get to the leaf. And so roots is level 0, while next chart of is level 1, as you see. Other terms that we can go over, it's all about again trees, so I'll go over all of them because you need to know this very clear and very good. So height of node is length of longest downward path to a leaf from that node. So if you want to say height of this is this, and height of this is longest path to the leaf. This is high. And also we have depth. So depth is of a node length of that path to root. So depth is opposite side. So depth of this is 1, and depth of this is this of this path. So it's going to be 4, for example. Number of edges. So technically by this we can say height of leaf is 0, height of root is maximum, actually is 3 high, and actually depth of leaf is 0, and depth of root depth of root is 0, and depth of leaf is high of the tree. And also we have other terms. If you know, and also if our tree is empty, then high gonna be -1. And an internal node. So what is the internal node? So you know, as known of we know it as call it also as an inner node, or in node as a short, or even branch node, is any node of a tree that has child node. So for this, any node that have child node is going to be inner node or branch node, or internal node. So this is internal, this is internal, but this doesn't have child, it's not. So external node, as also known as outer node, leaf node, or terminal node, it's a node that does not have child. So this one doesn't have child, so we call it external, and also we call it outer node, leaf node, and terminal node. And subtree. So any tree is a tree, okay? So any child of root's gonna be a subtree. This is a subtree. This is a subtree. So these are our subtrees. So as a definition, and neighbor, parents, or child. So to note that they are either parents or child of each other. They are they are neighbor. And ancestor, a node reachable by repeated processing from child to parents. So and ancestor from child to parents, any available node is ancestor, and from child to parent. Descendant, it's opposite side. Any node reachable by repeated processing from parent to child, also known as a subchild. Also we have branch node or internal node, a node with at least one child. Branch node, internal node, we had it up top. And degree, for a given node, its number of children. A leaf has necessary degree 0, so number of the children. So degree of this is going to be 2. So binary tree usually degree going to be 2. Degree of this is going to be 3 because we have 3. And distance, the number of edge along the shortest path between two nodes. So if we have a 2 node, for example this node and this node, distance is 2 because the shortest path is this one. And this node and this node, for example, gonna be 1, 2, 3, 4. So this is the shortest path. And okay, let's see anything else I can say. Distance, okay, level. The level of a node is the number of edges along the unique path between it and the root node. So number of edges between that node and root gonna be level of that node. So level of this. So level of A is 2, which is this number of edge between this node and the root, and so this level of actually E gonna be 1, 2, 3, 4, which is number of edge between. So this is about the level. And width, the number of nodes in one level. So number of nodes in each level gonna be width of that level, and yes, breed the number of leaves. So the number of leaves that we have gonna be you know, breed of that tree, and for us a set of n bigger than 0 disjoint trees, so trees that they are not joined to each other, and order tree, rooted tree in which an ordering is specified for the children of each vertex, and size of a tree, number of nodes in a tree, which is important because for any tree, number of nodes inside that, we're gonna say it's size of that tree. Okay, so that's it's about the terms, but most important part for heap is operations. So we categorize operations in heap, to basic, creation, inspection, and internal. So for basic we have find max and find mean, find max for max heap and find mean for mean heap, to find the maximum value, which is O notation 1. And for we have insert, adding a new key to our heap. Then after gonna be balancing and extract max or extract mean, which is return the node of maximum value for max heap or minimum value for min heap after removing it from the heap. So extract, we're gonna remove it and then return it. Delete max and delete mean, remove that, but we're not gonna return it. So same as this, but not return. Replace, pop, root, and push a new key. So usually for replace, we're gonna pop root and push the new one in there. More efficient than pop followed by push, since only need to balance once node, not twice. Add approach for fixed size of heap. So, and also creation, so we can create a heap, create an empty heap, and heapify, create a heap out of a given array. So we have an array, we convert it to heap, then this is heapify. And merge or union is join two heap to form a valid new heap containing all the elements of both, preserving the original heap. And meld join two heap to form a valid new heap contain all the elements of both, destroying the original heap. So merge, we keep original heap and merge them. Meld, we destroy original and merge them. Inspection, so we can return the size, number of elements in heap, and is empty if that heap is empty. And internal, increase key or increase key or decrease key, updating a key with a max or mean heap. And delete an arbitrary node followed by moving last node, and shifting, not shifting, shifting to maintain heap. Actually shifting, it's technically doing the same shift, so means that we're gonna shift, so we have shift up and shift down. In our implementation we do it as shift up and shift down, which is the moving a node up in tree. So we're gonna move it also as long as needed. Use to restore heap condition after insertion, we use this. And called shift because node moves up the tree until it reach the correct level. That's why we say shift. We could have said shift, but shift could be 1, but when we say shift, we mention that it's gonna go until get the correct level, as in sieves. And shift down is the same, move down until get the correct actually move a node down in trees, similar shift up, yeah, it just moved down, and used to restore heap condition after deletion. So this one you shift up usually after insertion, and shift down after deletion. Gonna be, let me highlight this because they're very important, or replacement. Okay, so these are operations, and in our implementation we're gonna go over this and implement them, or something like them. So good to know, heap are not stored. There are no particular relationship between nodes at any level. So in heap we just think about roots, which is maximum or minimum. And since heap are complete binary tree, the high of tree with n nodes has O log n height. So high of R2 is going to be O log n. So access to that one is going to be O log n as well. So when are heap useful? So this is the good question. So heap are used when the highest or lowest, as I said, highest and lowest order or priority element need to be removed. They allow quick access to this. O notation 1, as I say. And one use of heap is implement a priority queue. One of the uses is that we can, to create a priority queue, we use heap, not binary tree. We use heap to create a priority queue. Binary heap are usually implements using array, which save overhead cost of storing pointers to child nodes. And if we want to say something extra, so cons of using heap only provide easy access to a smallest or greatest item. Finding other item in heap takes O notation n time. Because the heap is not ordered, we must iterate through all the nodes. So cons is that for any other element except root, we need O notation n. So just use heap when you're looking for a specifically maximum or minimum value in your array, for example. And type of heap. We have lots of type of heap, and I mentioned some of them. And later I try to make a video for each. So 2-3 heap, B heap, heap, binary heap, binomial heap, brutal queue, the array heap, Fibonacci heap, KD heap, leaf heap, leftist heap, pairing heap, radix heap, randomized meldable heap, skew heap, soft heap, ternary heap, tree, weak heap. So 19 heap here I mentioned, and I try to explain each of them later. And here also I find of so one cheating sheet for time complexity. So for binary you will see for maximum of all of them is O1 is access find the max or mean. Delete is gonna be O log n, which is the high of R3, and insert gonna be O log n for binary or leftist, and ON for meld. This is the some guide to choose. Okay, this is good. That for what I'm looking for. If you're looking for insert, if you're looking for find max, or if you look for delete or whatever you look, then you can choose either of these heaps. Okay, so now it's time about implementing. So for implementing, let me make this a little bit bigger. Yes. Okay, so how can you implement heap operations in Swift? So there are these functions that we're gonna implement, and you know what, I'll go and implement, and later I will come back here and go over this if we need to clarify. If code was not clear, then we can come there back here and go over. So just here just a little bit give background to this. So shift up, shift down, and insert value, operation remove at index, replace index and value, search value, build heap from array, and heap sort. And technically just about time complexity, which is because it's important, I'll go over. And okay, so for heap time complexity, I start from heapify, which means creating heap. So time complexity of this is O log n. So O notation log n. So let me, make this, because we have a lot to say. Let me, so excuse me. Okay, so for heapify we said that for build heap, just time complexity gonna be on, just to build. And to get mean, so to get minimum in heap, time complexity gonna be O1, actually for mean heap. And of course for get max, for max heap gonna be the same. Gonna be the same for max heap. And that's why we make heap, or we use heap. To extract mean, time complexity gonna be O log n. And for decrease key, time complexity gonna be same, O log n. For insert, time complexity gonna be O log n. And for delete, time complexity again gonna be O log n. About a space, so heap space complexity is O1. And so of course all of this for all of this. N is the number of capacity or nodes inside Heap. Okay, so after time complexity, we jump to creating our heap. So what I do, I just say public because I want to make this available as a data structure. So I create public struct heap. I'm gonna make it generic, so from type T. So this is gonna be my heap, and here I start from variable nodes, which is equal an array of type T. Technically going to be empty at the beginning. Then I'm gonna create private variable by the name of order criteria T and T. That return boolean. And yeah, if I want to just write some description for this, just say determines how to compare two nodes. Technically, yeah, compare these two. And for max and min gonna be different. We'll go over later. Okay, private variable again. I'm gonna create another private variable. I name this one actually yeah, let's do this later. So I'm gonna create a public init. So to the constructor for this, I just say sort, because I want to init it. I want to say, okay, which order you want to. So I just use escape ping T and T to be boolean. And inside this, I'm gonna say, okay, self dot order. I just create here order criteria. Order criteria equal sort. So with this, we can create empty heap. Also, Here we mentioned that the sort function determine whether this is main or yeah. So how we can find its yeah, mean or max. So for comparable data types makes max heap, and smaller sign makes a mean. Okay. Now we will go after writing initial in it, then we can write another public init, and in this init we get one array from type of t. Also we get sort, again at escaping. Actually, this at escaping, I need to explain that this is a keyword. If we put it in function signature, says that this closure can escape, so it means that can finish later. So so this gonna be use of this to finish this later. We use this usually a lot, actually, for example, for data source or something that's loading image, when something take time and make finish after our function, we use this. So again, for this one, the difference is that this one just gets sign a sort that say that this is man or max or mean heap, but this one gets an array as an input as well. So configure heap from array, but we don't have this configure heap, we not defined it yet, but I'm gonna define this to create array from and actually create heap from one array. Other things that other private function that I make also, it is mutating function that configure heap, and just here I use that. So this one gets from array type of t, and inside I get nodes equal my array, and I say for excuse me, for I in stride with from nodes dot count divide by 2 minus 1, technically 1 and throw 0, so anywhere I start to 0 by steps -1. Usually we use CRID for when we want to create a range, from big to bigger start to small. So this one I just say shift down. What? I. So slowly, one by one, I shift down, each element to my heap. So another actually variable that property that I need to create is var is empty. If you remember in realize, so by this one I can find if my heap is empty or not. So what we do, just return my nodes dot is empty. If my nodes, so my array is empty, then it is going to be empty as well. Other one is variable count or size, so from type of integer, and this one return my nodes dot count, so size of my array, gonna return that. Okay, so let's see what else I need to do. I need to say, okay, add inline underline double underline always. I just say internal function, so this function name gonna be parents index and of index I from type of int. So for body of this, actually I need to say that this one return integer. For body of this, I just return I -1 divide by 2. Yeah. So just if I want to write explanation, actually some markdown for this, I just say return the index of parents of the element at index I. So return the index of the parent of the element at index I. The element at index 0 is root of the tree and has no parents. So just baseline is gonna be the element at index 0 is the root and no parents. That's why we say I -1 divided by 2. Okay, and later I'm going to talk about that's at inline and always. For now, let's zoom on our function. So other one is again at inline always internal function left child index of index should be together of index, again I from type of integer, and this one again return an integer. So this one return 2 multiple 1 plus 1. So you know, this is a tree, binary tree. That's why I use, you know, divide by 2, multiple 2, and you know, to calculate parent and left and right. So the other one that I'm gonna declare is right, and this gonna be plus 2 index. Yeah, this is how I you know, traverse my binary tree. Yes, and other function gonna be public function peak, that's so this one just return 1 t, which is optional, maybe not. Okay, so inside peak we just need to return nodes dot first. Okay, so about this at inline always internally, actually I just need to say that this is you know, some property wrapper that tell you know, compiler, actually send signal to compiler, depend of if you put always here or if you put never. So if you put always here, a signal to the compiler that to always inline the method, you know, approach this method inline. And if you put never, it means that signal to compiler that to never inline this method. So what is mean inline means that even though the compiler can make its own inline decision, and the inline attribute can be you know, used to force its decision. Okay, so yeah, that's about it. You can you know, Google it and learn more, but this is what I want to say. So we want to make this you know, our compiler you know, make decision inline when calculating this index or right, left, or parent. Okay, so let's go and continue our codes. We now gonna write our inserts. So first let me just write some description for insert. So this insert is add a new value to the heap. So this guy, I'm gonna add a new value to the heap. Okay, so what I'm gonna do, it's gonna be public as well, to be available for everyone, and it's gonna be mutating, so it's gonna change in you know, inside. So mutating a function. The reason we use mutating, because if you remember, our you know, heap is a struct, so that's why we have to use mutating. If it's class, then we don't need to use mutate. So we it's gonna say insert, what insert, underline to be broadcast, and so value of type of t. Yeah, and so we not return anything, we just update. What we update, we say, okay, our nodes dot append our value. So we append this value to our nodes value. Also, we're gonna shift up. Actually, that shift up means so nodes dot count -1. Okay. So this gonna be our insert. The other one, again, we're gonna do another insert, and this one adds a sequence. So I'm gonna make another insert that adds a sequence of values to the heap. Okay. So to actually just let me just write the complexity here as well. So with complexity, so what is the complexity for the single one? Is going to be O log n, and also it's going to be O log n for this sequence one as well. So what I'm gonna now, again, I'm gonna write a public method mutating, because it's not gonna return anything, just gonna update my array. So mutating function that inserts. So what gonna insert? So gonna insert, it's generic, so I use s, and I name from type of sequence. Okay, and so my function underline sequence from type of s. Actually, yeah, capital S. Yeah. And so here I just say where s dot capital I iterator dot elements equal t. So here I just say for value in sequence, what I want you to do, I want you to insert just top one value. Yeah. And so let me make this a little bit wider. If let me, it should be. Oops. Oh, not let me right now. Okay. So now just later I'm gonna define sequence as well. I'm gonna do it later. So for now, let me go over. Okay, so now I'm gonna write function for remove. So this function gonna removes the root node from the heap. Complexity gonna be same, O and login. And so what I say, or I just say at this cardable result. So what is this property wrapper for? This property wrapper actually say in case you didn't get value of this, don't give warning. So sometimes you see that you use some function that's supposed to return something and you're not gonna get it, then you get warning. So to avoid that warning, you can put this here, that if in case nobody take it, don't worry, do not bother me with warning. So return could be return optional. Okay, so to implement this, first of all, I'm gonna guard my nodes that is empty, otherwise return nil. So what this doing? So we mentioned that if our nodes is not empty, continue, otherwise return nil, because our nodes actually are heap is empty. Then we will go and count our nodes. So if nodes dot count equal 1, if it is already equal 1, I just need to return nodes dot remove last. Otherwise, I'm gonna use the last node to replace the first one. Then fix the heap by shifting or sifting. Okay, so I just say let value equal node 0. Then node 0 equal nodes dot remove last. Then I call function shift down. At the end, I'm gonna return value. So shift, I'm gonna put my last element where it's supposed to be. This is how easy we can remove. And O log n is our complexity. But another remove that we can implement gonna be, let me use same discardable, as I mentioned, discardable results. It's in case I don't want to use return value for this remove, I won't get warning. I make it mutating because it's a struct, and I'm gonna change my nodes inside this function. So at index from type of int, return optional value of t, which is my heap type as a generic one. Again, I use guard. This time index equal smaller than nodes dot count, then return nil. Otherwise, I'm gonna say okay, let size equal nodes dot count -1. Then I use if index not equal size nodes dot swap a and also index and size. So what I do, just say okay, if index is not equal size, not my bigger than my size, then I'm gonna swap my index and size actually with the end one. Then I'm gonna shift down from index until size. So from index until size, we're gonna shift down, and we're gonna shift up index. Okay, so this if will take care of our remove at index. And then I said nodes dot remove last, gonna be what I return. So I put my node at the end, I'm gonna return it, and I'm gonna remove it and return it. So by this way, let's just review it. So what we did, we just say okay, from our nodes, swap my index, I want to remove it, with size, actually put it at the end. Then I'm gonna shift down from index until size, until size of my heap. I'm gonna shift down, and then I'm going to shift up at this index, and at the end the item that I put in the last, I'm gonna remove it, which is gonna be remove at index. Okay, so this is for remove at index. Other function I need to write, I used it in top, it's gonna be internal mutating function shift up. If you want to name this shift up, you can go ahead, but you need to make sure to fix it in other function that you call it. So index gonna be from a type of integer. So what this do? It's very important actually for our heap. This is the function that will make our heap. So I just say okay, variable child index equal index. Okay, then let child equal nodes at index child index. Yeah, so my child gonna be this one. Then I'm gonna say okay, variable parents index equal self dot parents index of index child index. Okay, and so now this is the part that's gonna continue until our index goes to the correct location. So as long as child index bigger than 0 and order 3 carrier from child and nodes at index parent index, as long as this condition is true, our nodes at the index child index equal nodes at index parent index. Also child index equal parent index and parent index equals self dot parent index of index child index. Okay, so this is end of my function. Yes, so now at the end I just say my nodes child index equal child. So just let's review what we did. So this function takes a child node and looks at its parent. if a parent is not larger or not smaller. So not larger for max heap or not smaller for min, as long as it's not keep exchanged. So we exchange parent and child as long as it's not larger for max and smaller. So this is what we do here. We continue replacing our child and parent as long as it's not smaller, bigger. And what doing this parent index function. Okay, so this is our shift up. Other one gonna be our shift down. So internal rotating shift down. Actually, shift down gonna be from index, from type of integer until end index, until end index from type of int. So this is gonna be shift down. So what we do now, we just gonna say, okay, let left child index equal self dot left child index of index from index. So left child index, check it out, and then let right child index equal left child index plus 1. So then I just say variable first equal index, also if left child index smaller than end index and order criteria nodes left child index and nodes first. We use this order criteria to find out if we are max heap or min heap, and then we if this function gonna approach. Okay, So here inside this we just say first equal left child index. Okay, and we do the same for right. So sorry, yeah, if right child index smaller than end index and order criteria and nodes and right child index and first was true, then first gonna be right child index. So this is how a way we gonna do. And okay, what else I need to do? I just need to say, okay, if first equal index, then I want you to return because we're done. And also nodes dot swap at index and first. And also I'm gonna shift down. So I called same function, shift down from first until end index. Okay, so this is recursive, so we call it self. So let's come here and add some description as well to clear what we're doing. So we looks at a parent node and makes sure it's still larger for what? For max heap or smaller for min heap. Then even compare of its children. And we do this here, okay? Actually from here. Okay, yeah, so this is our shift down function. Okay, so we almost done. We just need to do one extension for search. So extension my heap structure where t is equitable. So where t is equitable, then extend it for me. Okay, so let me here also I write mark searching. Okay, so I'm gonna write the function public function index of node t. Okay, so this one gonna return one integer, which is our index, but this integer are optional because it's not guaranteed that we will return something. Okay, So this one return nodes dot index var. My operation 0, my operation first active operation equal no. So this is gonna be function of index, and this is a file. Actually, this is a function that gets the index of a node in the heap. Time complexity O n. But also I'm gonna write another discardable result, public mutating function by the name of remove that gonna remove node t. So this one removed by value, and you're gonna return t. So how are we gonna do this? We say if let index equal index of node. If you can find this index for me, then gonna return remove at index. Otherwise, return nil. So this function also removes the first, not all, the first occurrence of a node from the heap with the value that we want. And so time complexity gonna be O notation n as well. So first of all we say okay, make sure it is equitable, then go and search for node with this value. If this node exists at when I use var to find it, and that's why I say O notation n. This is a notation that's var need. If it exists, return. If not, gonna be nil, yes, because this gonna return nil. And here you are. Then this index gonna do that for us. So now we can remove the node with value, and also okay. So now then I finished this. Let me run it. Oh yeah, there is some error. One of them is here, says shift down. Oh yes, for shift down here we wrote on the test function. I need to write another function, another signature for shift down, which is an internal mutating function shift down. This one get only index from type of integer and not return anything, just shift down call shift down again, and in a way that say from index until nodes dot cut. Okay, so this one gonna get put nodes dot count for me. Also here, oh yeah, swap, one of them, I think I use swap somewhere. It is swap ads. So line 104. Okay, let's run. Okay, so left, excuse me, line 100, 136. Okay, so let me see. I think this left child I have mistyping. Yes, so left. I think all should be fine. Let me clear run. Yeah, only one index. Yeah, here I say if, so it should be equal. So I believe now I'm good. Yeah, here we go. No error. All good. So what I'm gonna do now, I need to test this. So when we have our heap completely completed, to test this, we can use one variable. I'm gonna do both max and min. So max heap, and I just say this is equal my heap, and from type of integer, as it was generic, and so this is max. So sort gonna be criteria, sort criteria gonna be this. So this is my max. Also I make one min heap, yeah, and then it's about to put a value value there. So max heap dot insert 30. Okay, so and here min heap dot insert 31. Okay, so what I'm gonna do, I'm gonna put okay, and okay, so here 31, 12, 1, 45, 6, 20, 50, and 9, for example. Okay, so I put same values here, 12, 1, 45, 6, 20, 30, 20, and 50, and 9. Okay, so now I'm gonna print it. So I just say print my max heap here, yeah, and here I just say print max heap. Min heap. Oops. Okay, so mean heap. Let's run it and see what's happening. Yes, it's working. Actually, the both are the same. Yes, for mean, I should say smaller sign. So yeah, here you go. So let me clear and run this. So you will see I made a max heap easily by and put variable in a different order, and at the end I have maximum number here. I don't care about the rest, I just care about this, and this is minimum number here. So then easily with just O notation 1 I can jump this and have maximum value in my heap. So of course there are some other function as a test. You can use them and see how they are working. So yes, that's it for today. I hope you like this video. Please make sure to give it thumbs up. Also subscribe in case you are interested for watching more video coming every week. And thanks you for watching. If you have any question, please put it in comment below. Any idea, anything that you think may be helpful for this channel. I wish the best for you. Have a good one. Bye bye.